Hello everyone, I'm Yuquan Du from the University of Sydney. Here I'd like to introduce our recent work, Quantum Differentially Private Sparse Regression Learning. This work is completed with Minxiu Xian, Tongliang Liu, Shan Yu, and Dacheng Tao. Quantum computing is a central technique in computer science. In particular, it can efficiently solve certain tasks that are computationally hard for classical computers. And in quantum computing, a central application is quantum machine learning. Quantum machine learning algorithms can, in principle, outperform the best-known classical algorithms when solving certain problems. For example, we have proved that quantum Boltzmann machine, quantum principal component analysis, quantum support vector machine, and quantum reinforcement learning are outperforming their classical counterparts, which achieve quadratic or exponential speed-ups. However, a central topic in both classical and quantum machine learning is private learning. Due to legal, financial, or moral reasons, the legality of the proposed quantum learning algorithms will be questioned if they cannot guarantee privacy. Differential privacy provides one of the most prominent solutions towards private machine learning. During past decades, many classical private machine learning algorithms are proposed. However, little is known about how to combine differential privacy with quantum algorithms. The formal definition of the differential privacy is as follows. Specifically, algorithm A is epsilon delta differential private if for any two neighboring datasets x and x prime, and for all matchable sets O, the following condition holds. And we can see this is inequality about the probability. Here, the neighboring datasets x and x prime refer that the number of rows in x that need to be modified to get x prime is 1. Intuitively, this inequality implies that when we input x or x prime into an algorithm, the output, the probability to get the output belongs to the matchable set O will be very similar. The basic idea of differential privacy is to randomize part of the mechanism's behavior to provide privacy. Introducing randomness to a learning algorithm is to make it hard to tell which behavioral aspects of the model defined by the learned parameters came from randomness and which came from the training data. As we can see in this figure, when the analysis query the server about the information of the database, the response adds some Laplacian noise, and the analysis cannot be identified the result is come from the real result or from the noise. A fundamental problem in private learning is differentially private sparse regression learning. Mathematically, let D be the given dataset, which includes the data X and the label Y. Suppose that the dataset D satisfies Y equals to X times theta star plus omega. Here, theta star refers to the underlying sparse parameters, where its sparsity is S, and omega is the noise vector. And in sparse regression learning, we have these following two conditions, where the sparsity is greatly less than the number of examples n, and the number of examples n is greatly less than the feature dimension d. The goal of the sparse regression learning is to recover the optimal parameter theta star. A mainstream learning model to tackle the sparse regression learning task is a lasso estimator. where the target parameter star is estimated by minimizing the following loss function. As we can see, this function measures the L2 norm description, this L2 norm of x times theta minus y. Here, the trainable parameter theta is constrained in an L1 norm ball that guarantees the sparsity of the estimated result. When we want to devise a differentially private lasso estimator, we need to attach another condition to this optimization problem. In particular, we should guarantee the differential privacy with, with respect to any change of the individual pair x, y, yi. The alternative measure of the private lasso estimator is the expected excess empirical risk. This is formulated by taking expectation over the object loss function with respect to the trainable parameter theta star minus taking expectation over the optimal result. Recently, Kunatawa proposed a classical private lasso estimator with the near optimal alternative bound RL. Well, his proposal is runtime requires expensive runtime, which scales with O n to 5/3 times d. The classical result motivates us to rethink how to design a quantum DP lasso estimator to solve the sparse regression tasks with privacy guarantee. Designing a quantum private lasso is challenged. The main challenges are due to following reasons. Specifically, quantum machine learning and deep learning have different aims, where the former pursues a low runtime cost, while the latter concerns a low activity bound RL. Therefore, the proposed quantum DP lasso should accommodate the following requirements from each side. First, the runtime cost should outperform its classical counterparts and cannot be dequantized by quantum-inspired classical algorithms. Second, the achieved activity bound is expected to be near optimal. Our contribution in this work are as follows. First, we design a quantum differentially private lasso estimator which achieves a better runtime complexity than the optimal classical lasso and a near optimal activity guarantee. Second, we prove that the runtime complexity of the proposed quantum DP lasso can be even lower than the optimal non-private quantum lasso estimator under certain conditions. As we can see in this lemma, we prove that the runtime complexity of the quantum non-private lasso is lower bounded by square root n plus square root d. But for the quantum DP lasso, the runtime is independent of the feature dimension d. This implies that when n is less than d to 1/5, the runtime of quantum DP lasso is less than quantum non-private lasso. Before presenting our algorithm, we first address the classical and quantum input models used in our paper. Specifically, to make a fair comparison, the employed quantum input model are restricted to have an almost identical setting to the classical case, except that we allow coherent queries to the entries of given inputs. This is different from QRAM. In other words, our result cannot be dequantized by quantum-inspired classical algorithms. Two components in our quantum DP lasso estimator is quantum non-private lasso estimator plus quantum privacy mechanism. As we can see, when we use quantum non-private lasso estimator to learn the dataset X and Y, we attach a privacy mechanism to prevent the adversary to get the private information of the dataset. We now explain the proposed quantum non-price lasso estimator. In particular, it's a quantum generalization of the classical Frank-Wolf-based lasso estimator. And the runtime cost and the Article bound is described in this theorem. As we can see, the Article bound of the quantum non-price lasso estimator is inverse to the iteration number t with an additive error var sigma, and its runtime scale with the number of iterations t and the number of examples n and the feature dimension d. We first recall the classical Frank-Wolf based lasso estimator. As we can see, this algorithm is repeat the following procedures with t times. In particular, at each iteration, we project the gradient of the objective function L to all its basis components to form a vector alpha t, and then we search the index corresponding to the minimal entry of the alpha t. And when we locate this index kt, we update parameters, or we only update this kt's entry of the trainable parameters. An illustration is given in this figure. As we can see, at each iteration, we locate the vertex corresponding to the minimum entry, and we update the parameters along this direction, and so on. So in this method, we can guarantee the sparsity of the trainable parameter theta t, namely in t iterations, the sparsity of the trainable parameter theta t is at most t. We now generalize the classical Frank-Wolf algorithm to the quantum case. As we can see, we only modify two parts, namely, we use quantum oracles to prepare a quantum state corresponding to the alpha t, and we use quantum minimal finding algorithm to locate the index corresponding to the minimum entry of alpha t. Notably, both the implementation of alpha t and the runtime of the quantum minimum finding algorithm is very low. As for the implementation of the oracle ORT, we can see its runtime complexity scale with t squared times square root n. And as for the runtime complexity to find the index kt, the result of quantum minimum finding algorithm implies it scales with the square root of the feature dimension d times the runtime to prepare the oracle ORT. When we have the quantum non-private lasso estimator, we design a privacy mechanism to provide the privacy guarantee. The key insight of the proposed weight sampling privacy mechanism is as follows. Instead of seeking the index corresponding to the minimum entry of our t, the weighted sampling algorithm exerts randomness on output, where all index can be selected and be the index where corresponding entry is close to the minimal entry will be selected with higher probability. Mathematically, the weighted sampling privacy mechanism is as follows. We use the oracle alpha t to prepare state w alpha t. As we can see, the index corresponding to the minimum entry will be sampled with higher probability, and the index corresponding to the largest entry of alpha t will be sampled with lowest probability. So in the training process, we directly measure the index register S to introduce randomness to the algorithm. And this is the whole algorithm of the proposed quantum private lasso estimator. And we can prove that when we substitute the quantum minimum finding algorithm with this randomness, it achieves runtime speed up and it attains optimal activity bound. And we now summarize our results. First, we propose a first quantum private learning algorithm with runtime advantages and a near optimal activity guarantee. And second, the runtime complexity of the proposed DP lasso with a weighted sampling mechanism outperforms optimal classical lasso estimator and can be even lower than the optimal quantum non-private lasso. And our future work is exploring how to use this device to apply DP learning models. Thank you.